Okay, we're picking up with example 7, and I'm going to run through this a little faster than some of the other ones because I think you kind of have the hang of it now. And so this is where we want to find a region bounded by the y-axis, find the area of the region bounded by the graph of f of y is equal to y squared, and the y-axis for the interval from 0 to 1 along the y-axis, okay? So what we're going to do is the same kind of thing here. I'm going to say what y sub I is, and we're going to start at where you start at 0. And then plus, I'm going to use an I times, then I've got my delta y, if you will. So delta y in this case is then going to be 1 minus 0 over n. So it'll be I times 1 over n. So remember that's A, this is A plus I times delta x. So now it's delta y, okay? All right, so we have our expression then. So y sub I is equal to I over n. Okay, so then we've got our area is equal to the limit as n approaches infinity of the summation of f of y sub I, 1 to n. So this is going to be f of I over n times 1 over n, your delta y. It's right here. So we get the area is equal to the limit as n approaches infinity of the summation from I is equal to 1 to n. So f of I, so the function is y squared. So f of y sub I. So it's then going to be y squared. So it's going to be I over n squared times 1 over n. Okay. So we get the area is equal to the limit as n approaches infinity of the summation. So from I is equal to 1 to n, then this is going to be I squared over n squared times 1 over n. And so we get this area then is equal to the limit as n approaches infinity of the summation from I is equal to 1 to n of I'm going to scooch this out a little bit, and I'm going to pass the n cubed in front of the summation 1 over n cubed, n squared times n, and then I have the summation of I squared. Okay, so with this we get then 1, the limit as n approaches infinity of 1 over n cubed, and then I'm just going to multiply times n plus 1 times 2n plus 1 over 6. Oops, over 6. And so you can kind of see that the focus here is the leading terms of that polynomial, right? So I've got the limit as n approaches infinity of this 1 over, so it's going to be 2n cubed plus 3n squared plus n, right? Over 6n cubed. So like I said, after a while, you kind of get used to this and 6n cubed, right? And so sometimes I would just write 2n cubed over 6n cubed and then be done with it. So here you can see that we get 2 over 6, or it's equal to 1/3. So this area is 1/3. And this should be reasonable to you because we just calculated the same thing in a way with the function f of x is equal to x squared. We got 1/3 for an answer. So it really doesn't matter the variable, even though the area looks a little different, you know, still a congruent area equal to 1/3. So here is the area that we calculated. Okay, and one last problem with this. We have approximating the area with the midpoint rule. So you can kind of see that if you wanted to, you have a center of each subinterval that is, for instance, the first one, c sub 1 is equal to x sub 0, which would be right here, right? That's your a value. And then x sub 1 would be pi over 4. So we would find c sub 1 by adding the two x's together and then dividing by 2, finding the average to get pi over 8. So what I have is my c sub 1 is pi over 8, c sub 2 is 3 pi over 8, c sub 3 is 5 pi over 8, and c sub 4 is going to be 7 pi over 8. Makes sense, right? Pi over 8 is the counter, and kind of get used to the idea of fractions. Sometimes people look at pi over 8 and like, So if this is pi over 8 for c sub 1, then pi over 4 is 2 pi over 8. C sub 2 is 3 pi over 8. Pi over 2 is 4 pi over 8. C sub 3 is 5 pi over 8. So you just use the pi over 8 as a counter, if you will. Okay, but remember, your C's are the center of a subinterval. All right, so if we have the area is equal to, or is approximately equal to, then I'm going to say that this area approximately equal to that is equal to, then the summation, I'm going to use 4 subintervals for this. So I have I is equal to 1 to 4 of, it's the sine function. So f of x is equal to the sine function. So I'm just going to write sine of x sub I. And oh, I guess I use c sub I in this case, because it's the center of each subinterval. So I'm going to use c sub I. Okay, and then I'm going to multiply that times delta x. Delta x in this case is then going to be pi minus 0 over 4, so pi over 4. So with this, then I have pi over 4 times the summation of this sine of c sub I from I is equal to 1 to 4. So that's equal to then pi over 4. And we can say f of c sub 1 if you wanted to. F of c sub 1. Oops, so c sub I here. C sub 1 plus f of c sub 2 plus f of c sub 3 plus f of c sub 4. I pass the pi out front, so I'm not really doing the product of the delta x times that. I'm pulling the delta x out, pi over 4. And so then I get pi over 4 times the sine of pi over 8, sorry, pi over 8, plus the sine of 3 pi over 8, plus the sine of 5 pi over 8, and the last one, the sine of 7 pi over 8. Okay, just using that midpoint. So we get an approximate area with all these of 2.052. Okay, and you can use a calculator for this if you like to kind of confirm your answer. Okay. All right, so that's the last example problem in section 4.2. I hope you enjoyed this section. I think, like I said, it kind of becomes mathematically artistic. So if you like the math, you like the language, and you enjoy the proceedings here, then good. I hope you do. All right, and I will see you guys tomorrow. This is the last video, 4.2 area, and I'll see you when I see you. Take care.